Okay, let's solve this problem. We have a rigid container has 5 kilograms of saturated liquid vapor mixture. So we have phase change process number 3, saturated mixture. The mass is 5 kilograms. And pressure P1 is 150 kilopascal. Initially, 3/4 of the mass is in the liquid phase. So from here, we can determine the quality X. So how can we determine quality X? Quality X is mass of vapor over mass of liquid plus mass of vapor. So what is the amount of the liquid? 3/4. So 0.75 is in the liquid phase, and 25%, 0.25 is in the vapor phase. So what is the quality X? 0.25. So we know pressure and quality X. So the initial phase, initial state is no problem. Then we have an electric resistance heater is going to provide work into the system. How much? I don't know, but we know it's going to be provided until all the liquid in the tank is vaporized. So that means the phase change process at the end of the final state is going to be saturated vapor. So what we want to do is that we want to determine the entropy change of the steam during this process. So how can we determine the entropy change? We can calculate the entropy change by mass times the specific entropy at the end of the process minus the specific entropy at the initial state. So that's how we can determine the change of the total entropy. Then we know the mass is 5 kilograms. Then can we determine S1? Yes, we can. How can we do that? We know it is phase change process number 3. If you know it is phase change process number 3, we can use linear interpolation equation to determine this S. So S2 is going to be SF plus quality X, talking about S1, times SG minus SF. So what is SF? We can find this SF and SG from 150 kilopascal. So let's go to 150 kilopascal. So there is a table at 150 kilopascal is this one. So what is SF? 1.4336 is SF. 7.2233 is SG. So we have SF and SG. 1.4336. 7.2233 is SG. Then what about the quality X? 0.25. So can you determine S1? Yes, you can. S1 is going to be, do I have it? 2.881. 2.881 kilojoule per kilogram Kelvin. So we got S1. 2.881. That's what? Because we want to determine the entropy change. So if you want to determine entropy change, you need to be able to calculate the entropy at the initial state, S1, and the entropy at the final state, S2. So now, can you determine S2? Unfortunately, no, because we only know it is a saturated vapor. We don't know the pressure. We don't know the temperature. So what do we do? Oh, we give up? No, no. One thing we know is it is a well-insulated, rigid tank. What is the characteristic of this rigid tank? Its volume V remains constant. So if you can calculate volume V from the initial state, that volume V is the same as the final state. So we can find the specific volume at the end of this process. If you know the specific volume and you know it is phase change process number 4, then this one is going to be Vg, the saturated vapor. Then you can calculate entropy S, because entropy S2 is going to be also Sg. So if you know Vg, you can find Sg. That's our plan. So let's do that. We want to determine the specific volume. How can we do that? Since it is a phase change process number 3, we can use the same equation. V1 is Vf plus quality X, Vg minus Vf. Vf is this one, 1.0528 times 10 to minus 3. Quality X is 0.25, right? 0.25. And Vg is this one, 1.159. So can you determine V1? Yes, you can. If you do the calculation, V1 is going to be 0.29054 cubic meters per kilogram. And since we know at the end of this process, the steam exists as saturated vapor, since it is a rigid container, V1 is the same as V2, and V2 is saturated vapor, so we can say this one is Vg. So where is Vg? It's right here. So can you find this number on this table? Yes, it is between 0.31, 0.27. So what is Sg? It's going to be between 6.76 and 6.70. So can you determine Sg? Yes, by using linear interpolation. If you don't remember how to do linear interpolation, let me do the last time. So the left-hand side is Vg. The right-hand side is Sg. So what is the two numbers? These two. 0.3157, 0.2729. And what is the corresponding Sg? 6.7600, 6.7080. Then, what is the specific volume? That's 0.29054. 0.29054. What is Sg at this Vg? Is this one. Then what about here? 0.2729. Sg 6.7080. If you solve it, can you determine Sg? Yes. What is Sg? 6.72943 kilojoule per kilogram Kelvin. That is S2. Then this number Sg, S2 goes here. S2 is going to be 6.72943. Now, can you determine the change in total entropy? Yes, we can. It is 19.24 kilojoule per Kelvin. Huh? This problem? Not necessarily something similar. The concept? Possibly. We are just solving a simple closed system. It's just, we are studying how to evaluate entropy S. So, what we learn from this problem, when we have a phase change material such as a steam, we can use a table to evaluate entropy S. So when you have a phase change process number 3, we used linear interpolation to determine specific entropy S. When you have a steam or refrigerant such as R134A. So when you have water or refrigerant, you can assume it may undergo phase change. So use your common sense to determine whether there is a phase change or not. What about if this cell phone, your system? If this cell phone, your system, is there phase change? No. So that's a pure system. If you have a steam, not this water, but let's assume that this one is boiling. Is there the phase change? Yes. Then you need to use a table. If it is a solid like this one, we know there is no phase change. Then you use the entropy. You are going to use an equation to determine entropy that we are going to study today. What about air? Is there phase change? Not really, right? We have air, it's a gas, and it's going to be gas tomorrow. It's going to be gas, but day after tomorrow, then it's going to be pure gas. Then you don't use a table, okay? And between phase change material and pure system, we studied phase change system. When you have a phase change system, we use a property table. When we have a pure system, we don't use property table. We use equation. That equation is what we are going to study today. Yeah, you can have it. So let's see, what kind of equations are available to determine entropy S of pure system. We can start from what is called TDS relation. So we are going to study TDS relation. Don't worry, this is the first time you see this one. So it may be a little bit complicated, but this one is very simple. If we follow, if you follow, what I do. We are going to talk about how entropy changes, from the most widely used equations, governing equations in thermodynamics. What is the most widely used equations that we studied in this course? Ideal gas? Yeah, we used ideal gas a lot, but there is one equation that we used more often, energy balance equation. So let's talk about energy balance equation. There are two energy balance equations that we studied. The first one is a closed system. The other one is an open system. So let's go with the simplest one, a closed system. What is the energy balance equation for closed system? Q in plus W in minus Q out minus W out is going to be U2 minus U1, mass times U2 minus U1 plus moving boundary work. Oh, this one looks too complicated. Let's simplify that. How can we simplify this equation? We can combine Q in and Q out. Then how do you combine Q in and Q out? I'm going to say net heat transfer Q is going to be Q in minus Q out. We can also combine W in and W out. How? Net energy transfer by work W is going to be W in minus W out. Sounds right? But in thermodynamics, we say W out minus W in, because that's what people did 200 years ago. Because in 200 years ago, we first studied heat engine. So we want to make, the steam-powered train or locomotive or something. So our focus was how much fuel we need to, consume to create how much work. So our focus was how much fuel we need to consume and how much work we can produce. So our focus was W out and Q in. That's why, when we calculate net energy transfer by work, it's going to be Q out minus Q in, rather than W out minus W in, rather than W in minus W out, because our focus was on W out at the time. It's like plus minus when you talk about electric system. The electrons come out from positive and go to negative, right? Now the other way. Now we know it goes the other way, but long time ago, people thought that it comes from positive and go to negative. Now we are still using the same concept. The same thing in thermodynamics. Long time ago, people focused on Q in and W out. Do we want to change? No, we stick to that. So that's why we calculate net heat transfer. It's going to be Q in minus Q out. When we calculate net energy transfer by work W, it's not W in minus W out. Sounds reasonable in mathematics? No, but in thermodynamics, we say W out minus W in. If you're not happy with that, you can go to and find Isaac Newton, where's his graveyard, and complain. Okay? And we can also simplify this one, assuming that I'm going to say there's no moving boundary work. Then there's a mass. Oh, I don't like mass. So what do you want to do? I want to, let's talk about that later. Oh, I can combine these two and say this giant U, big U, minus total internal energy, U2 minus U1 is going to be Q, net heat transfer Q, minus net energy transfer by work W. So this is the energy balance equation. Okay? They are the same thing. Oh, I'm going to say there's no moving boundary work, or you can combine WB and W out. When we studied moving boundary work, that moving boundary work was a part of W out. We placed that on the right-hand side because it is a part of total energy change. But it is actually, a part of W out. So it just depending on, the way you want to put it in. So now, let's talk about something interesting. Now we want to calculate entropy. What is the definition of entropy? You don't remember? That's okay. I'm going to let then you know the definition of entropy is the change in entropy is going to be del Q over T when it is internally reversible. If you don't remember this equation, then go back to the first slide, first PowerPoint slide. You all have it, right? You go to Blackboard, you can download it. Please download and print it out. Don't study, the book from page 1 to page 1000. It's gonna take years, right? So, when you look at the definition of this entropy, one thing you can notice is that this looks different from this one. What is the main difference? This is in a differential form. This one is not. So why don't we convert this one into a differential form? Can we do that? That's simple. You just need to say, oh, it's not now, it's not just Q, it's gonna be the change in Q. What is the change in Q? Difference in Q and difference in W is going to be difference in U. However, this equation is incorrect because Q and W's are path function and U is point function. So when you have a point function, you can add D, no problem. But if you have a path function, you don't want to put D, you want to put there. Just to show that this is a path function. There. This one. Del Q minus del W is going to be the difference in U. This is the differential form of this energy balance equation. This energy balance equation is from this. Okay? Nothing new. We're just, we just come up with the main energy balance equation that we studied in chapter 3, and we simplified that and then converted that equation into a differential form. Now, we are going to apply this equation on a reversible process. Then, I don't like this there. I want to, change it because you cannot calculate this simply in mathematics. You can simply calculate this D, but not there. So what do you want to do? I want to replace this there with D. Is there any way? Is there any equation that has del Q? Yes, there is one. This one. ds is del Q over T. So if you multiply by T, what do you get? TdS is del Q. Now you see TdS. Because of this, it is called TdS relation. Not very creative, right? So del Q is TdS. Okay, I'm going to replace this del Q with TdS. No problem. What about this del W? What is del W? The change in work. Do you know how to determine work? Yes, how? How to determine work? What is the, just tell me any simple equation you can use to determine work. What is work? Like, what is velocity? Distance over time, right? What is work? You can do either pressure or force. Pick one. Force times. What is work? Force times distance. So work is force times distance. F times ds, distance. Oh, wait. There's a S. This is entropy. This S is distance. Oh, that looks confusing. So I'm not going to do that. Force is pressure times area. Pressure times area times distance. Now, area times distance. What is it? What is area times distance? area times thickness. Volume, yes. Pressure times area times distance is pressure times volume. PdV. Del W is PdV, pressure times volume. So this one is pressure times volume. Why it is not PV? Why it is PdV? Because it's a differential form. PdS minus PdV is du. Okay, nothing new, but now we don't have this complicated there. We only have this d. Calculating this d, solving this d is super simple. If you're not 100% sure, I'm going to show how easy it is, okay? But there's one thing. What do you want to calculate from here? Do you want to calculate T? Do you want to calculate T, V, U? Which one? Yeah, it depends, but you know, what is the subject here? No, I mean, what is the property that you want to evaluate? D? D is not a property, it's a differential. Yeah, what is the property that you want to calculate here? S, you're right. So there's our S, ds. Then, if you want to calculate this S, you want to move everything to the other side, right? Reasonable? Yeah. So let's move this one to the right-hand side. And there's a T in front. So how can you get rid of this T? Divide by temperature. Divide by temperature. Divide by temperature. So what do you get? ds is du over T plus PdV over T. Then do you remember from chapter 1 of thermodynamics, I told you, you want to use intensive property rather than extensive property. This capital S, do you like capital S? Now you want to have lowercase s, specific entropy. How can you convert this capital S into lowercase s? Time divided by mass. Yeah, divided by mass. Oh, divided by mass. Divided by mass. Divided by mass. Then what do you get? Lowercase ds is du over T plus PdV over T. Now, we want to calculate this S, but this is not just S. What is next to it? D. Now, can you remove this D? It's a differential form. How can you get rid of this D? Yes, you want to integrate. From where to where? It's a process, so it's going to be initial process, initial state to a final state. What is the initial state? 1. What is the final state? 3, 2. Yes. So from 1 to 2. From 1 to 2. Now, what is integral ds? From 1 to 2. What is the solution to the left-hand side? No. S2 minus S1. When you integrate x dx from 1 to 2, what is it? X2 minus x1, right? Then, what about this s? S2 minus S1, am I right? Yes. Then, can you integrate du over t? Du over t? How? What is the answer? Can you integrate du over t or not? Yes and no. The answer is no, because if this t is constant, this t comes out, then you can integrate it. It's going to be u2 minus u1. But we do not know the relation between u and t. So until you find the relation between u and t, you cannot solve this one. Then, do we know any equation that has u and t together. Any equation that you studied that has u and t. We studied one equation in chapter 3 that has u and t together. What is it? Classification equation. U2 minus U1 is CVT2 minus T1. So there is U and T, right? Right? Then, now, this one is a differential form. Is this, differential form? If it is differential form, you need to have D. Is there a D? No, so this is not a differential form. Then what is the differential form of this one? D means difference. Difference in U, U2 minus U1, du is going to be CV, difference in T, ET. So du is CV dt, is the differential form of this equation. Always, think about D as a difference, then it is easy to, the switch, convert between a differential form and the normal form. Then du is a CV dt. Now there's a du. Then can we say this du is a CV dt? Yes. So it's going to be integral from 1 to 2. CV dt over t plus integral from 1 to 2 pdv over t. Now, can you integrate this one? Can you integrate this one? Yes or no? CV dt over t. No, you're right. We can't, unless we know the relation between CV and t. Then, what about if we assume CV is constant? If you assume that CV is constant, now can you integrate this one? Now, yes. Why? If this one is constant, this one comes out. So this equation becomes S2 minus S1 is CV natural integral from 1 to 2 dt over t plus, what about here? If we talk about solid, pure solid and liquid, what is the main difference between pure gas and them? What is the difference between pure gas and solid, pure gas and liquid? There are many, many differences, but one thing that we used, very common, they are incompressible. The volumes remain constant, practically. Solid volume remain constant. Liquid volume remain constant. Air volume is not constant, right? So if you say your system is either solid or liquid, what is the change in volume? This du means change in volume. What is the change in volume when you have a solid or liquid? 0. Then, can you integrate dt over t? If you don't remember the mathematics, let me show you. Integral dx over x from 1 to 2 is going to be natural log x from 1 to 2. That means natural log x2 minus natural log x1. That means natural log x2 over x1. Okay? So this one is dx over x. We have dt over t. They're the same thing. So what is the equation? S2 minus S1 is going to be CV natural log T2 over T1. So this is how you determine entropy change of a solid or liquid. Any question? When you have a new equation that contains T, you should have one question. What is it? What unit is this? Celsius? Kelvin? It should be in Kelvin. So whenever you have a solid or liquid, that's how you determine entropy change. Then now, one final question. Do we have to memorize all of them? Not really. Write it down on your formula sheet. I'm just showing you that this is not out of the blue. This is from the energy balance equation. So if you want to determine how much entropy changes for a pure solid or liquid, this is how you determine that. As long as you know the temperature, initial temperature, the final temperature, and specific heat, you can determine entropy change S2 minus S1. They should be in Kelvin. T1 is the initial temperature, T2 is the final temperature. So this is, the one example of what? TDS relation. And why we say TDS? Because this one, TDS relation. And that's not the only TDS relation. There are more coming soon for pure gases. But this one is only for pure solid and liquid. Now you know how to determine entropy change for two different systems. The first one is phase change material. You use a property table. And second, when you have a solid or liquid, you use that equation. The last one is going to be pure gas. That's what we are going to study later today. Okay? So since we studied one equation, let's solve one problem together. To understand this problem and to understand this equation, okay? To understand, how to use that equation. So we have a 75 kilogram copper block initially at 110 degrees Celsius. It's dropped into an insulated tank that contains 160 liters of water at 15 degrees Celsius. Please determine the final equilibrium temperature and the total entropy change for this process. So we have a solid, we have a liquid. So I guess we can use the equation we just studied. So let's do that. First of all, we want to determine the final temperature. How can we do that? We can use energy balance equation. Whenever you want to determine a property other than entropy, you use energy balance equation. What about entropy? Then use entropy balance equation, but we haven't studied entropy balance equation yet. Okay, so just energy balance equation. Then, what is the energy balance equation? There are two energy balance equations, one for a closed system, the other one for an open system. So you need to determine whether it is a closed system or an open system first. We have a copper block. How do we know whether it is a closed system or an open system? The question is going to be, whether the mass of the system changes or not. If the mass is constant, it's a closed system. If mass is changing, it's an open system. What about this copper block? The mass changing? No. Water. What about the mass of the water? Does not change. So both of them are closed system. So then what is the energy balance equation for a closed system? We have two systems, copper block and water. So copper block first. Cu is copper block. And what is the energy balance equation? Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. So are we going to use this equation as is? No. What about moving boundary work? It's a copper block. Is there volume change? No. The moving boundary work is going to be 0. This copper block is at 110 degrees Celsius, and now it is dropped into water at lower temperature. So what do we expect? There is a heat transfer, right? From where to where? From the copper block to water. So copper block, there is a heat transfer from the copper block to the outside. So we have a Q out. That is the heat transfer Q. I don't know how much heat transfer is it, and we can neglect the other three. And how do you determine this one? Mass times specific heat times T2 minus T1. So that is the energy balance equation for this copper block. Then now we have one more system, that is water. Then what is the energy balance equation? Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. Then what is the moving boundary work of this water? Water is liquid, so we neglect any volume change. The water is receiving heat from this copper block. So there is an incoming heat transfer for the amount of what? Q. This Q should be the same as this Q. And there's no energy transfer by work. Water is at the lowest temperature, so there is no heat transfer from the water to the surroundings. And how do we determine this one? Mass times specific heat times T2 minus T1. So the copper block is dropped into water. It is hot, so it is going into water. The water temperature goes up, right? So water is receiving heat. So now it's time to combine these two. We know this Q is the same as this Q. So let's replace this Q with this one. So we have a negative sign in front, minus mass of water times specific of water times the temperature, the final temperature, minus the initial temperature of water is going to be mass of copper times specific of copper times temperature, the final temperature minus the initial temperature of this copper block. This one? Because there's a negative sign. So this Q in for water is the same as this Q for this copper block. So this one is the same as this one. This Q is mass times specific heat T2 minus T1. So we can, substitute this one for this Q. Make sense? So this blue is for water. This red is for the copper block. Then what is the mass of water? Let's see. Oh, we don't have the mass, but we know the volume. Then can you determine the mass? Yes, no problem. Mass is density times volume. What is the density of this water? The density of water is a function of temperature. So let's select the room temperature, and the density is going to be 996.5. So this one is 996.5 kilogram per cubic meters. What about the volume? The volume is 160 liters. 1,000 liters is 1 cubic meter, so it's going to be 0.16 cubic meters. What about the specific heat? Do we know the specific heat of water? Yes, we can select the specific heat at 300 Kelvin, 4.179. So this one is 4.179 kilojoule per kilogram, degrees Celsius. What is the final temperature? Unknown. What is the initial temperature of the water? 15 degrees Celsius. What is the mass of the copper block? 75 kilograms. What is the specific heat of the copper block? 0.385 kilojoule per kilogram degrees Celsius. What is the initial temperature of this copper block? 110 degrees Celsius. Then this T2 is unknown. And now we have one equation. How many unknowns? 2. This T2, this T2. Do we have 2 unknowns? No, they are the same. The final temperature of the mixture should be one temperature value, right? So the final temperature of the water is the same as the final temperature of the copper block, right? When it is in thermal equilibrium. So you can solve this equation to determine T2. If you do, you get 19 degrees Celsius. So that's how you determine the final equilibrium temperature of this copper dropped into water. Any question up to here? Now, this is not the end because we only calculated the final temperature. What we want to calculate is the change of entropy. How do we calculate the change in entropy? Change in entropy can be determined by change in entropy of copper block plus the change in entropy of water, right? Because we have 2 systems. If you want to calculate the total entropy change, you need to calculate the entropy change of each system and calculate the sum of these 2. So how do we determine the change in total entropy of copper block? Use this red. Mass times S2 minus S1. What about this water? Mass times S2 minus S1. What is the equation? We just studied from this TdS relation. S2 minus S1 is what? Specific heat, natural log, T2 over T1. Specific heat. C, natural log, T2 over T1. What about this water? Mass times specific heat, natural log, T2 over T1. So, what is the mass of this copper block? 75 kilograms. What is the specific heat? We already found it, 0.385 kilojoule per kilogram degrees C. The initial temperature of the copper block, 110. 110. The final temperature of the copper block, 19 degrees Celsius. What about the mass of the water? This one times this, 996.5 kilogram per cubic meters times 0.16 cubic meters. And what about the specific heat? This one, 4.179 kilojoule per kilogram degrees C. The initial temperature, 15. The final temperature, 19. So that's how you determine the change of entropy of each system. Is that right or there's a mistake? Yes, Kelvin. You're right. So this one is not, it should be 291 Kelvin. This is not, it should be 383 Kelvin. What? Oh, 292. What am I doing? So this one is 292 Kelvin. This one is 283 Kelvin. So if you do the calculation, you get this one to be minus 7.85 kilojoule per Kelvin. This one is 9.1, 7.83, 9.19 kilojoule per Kelvin. So what is the sum of these two? You get 1.36 kilojoule per Kelvin. So having a positive entropy change, what does it mean? It means it is not a reversible process. It's an irreversible process because there's an increase. It means that useless energy is created. So you cannot go back. If you have a reversible process, this one should be 0. If this one is a negative value, what does it mean? It's an impossible process. Any question? 0 reversible, negative is impossible, positive is possible. Then you may have a question. Oh, there is a negative sign. So is it wrong? Not really. Locally, entropy can go down, but the sum cannot go down. Any question? Is it too difficult? Really? Not really, not really, right? What? Yeah, right. So thermodynamics is not just, the one chapter by chapter. It's like, the complete package. So if you didn't do well in your first exam, what you need to do? Go review. Make sure that you have 100% understanding. Otherwise, the second exam is going to be harder than that. Otherwise, the third exam is going to be harder than that. Yes. Oh, the deriving these equations? No, not at all. Then why did I show you? You got to know where it is from, right? So it's not from out of the blue. It is from the energy balance equation. So now we studied how to determine entropy change for solid and for liquid and for phase change material. Then what is the last one? Gas. But this one is slightly more complicated. So please, there are not just one equation, there are many equations. So don't worry about that. Nothing is new. Everything is from the same equation, energy balance equation. Okay? So I'm going to derive 3 equations. Then what do you need to do? You got to understand, that these are not from out of the blue. These are all from the same energy balance equation. But why do we have 3 different equations? Because, that depending on the case of your problem, you need to select, the one among 3. Because not every 3 is going to be at the same level. You can use it, but the one will be easier than the other. And how do you know, this one should be easier than the other 2 equations? You got to know how I derive them. Okay, some equations are the same as the previous. So let me find this one. Okay, from here, which one? Which one? So we started with this energy balance equation and found the simplest one, and then converted in the differential form and got rid of this del and replaced them with this d. So let me start from here, okay? TDS relation. Let me start from here. TDS is minus TDV is du. So from this energy balance equation, we learned TDS relation. That is TDS minus PDV is du. So that's the starting point. Now our system is what? Gas. Then we want to calculate this entropy change. So to determine this entropy change, we want to move this temperature to the other side. And we want to move this one to the other side. So divide by temperature, divide by temperature, divide by temperature. And we want to divide by mass too. Mass, 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 T and M, temperature, mass. Oops. Then this one becomes ds is du over T plus PdV over T. Now let's calculate entropy change. How can we do that? We can integrate from 1 to 2, from 1 to 2, from 1 to 2. Then the left-hand side is simple. There's nothing here, so it's going to be S2 minus S1. There's nothing here? No, there's a 1 over T. That's a problem. So how can we solve this one? I'm going to make an assumption that is specific heat, CV and CP, they are constant. Specific heats are constant. Then we know U2 minus U1 is CV T2 minus T1 from chapter 3. So this equation can be written as du is CV dt. The change in U2 minus U1, is going to be the change in temperature, T2 minus T1. And we know there is another specific heat equation, H2 minus H1 is Cp T2 minus T1. And the differential form of this equation is going to be dH, the change in H, H2 minus H1 is going to be Cp times the change in temperature. Then we have a du here. Du here, can we put this one in this equation? Yes. Then this equation becomes 1 to 2 Cv dt over T plus from 1 to 2 P over T dV. Now, since we assume that Cv is constant, this one comes out. Then integrating dt over T is simple, because we know the integration of dx over x is going to be natural log x2 over x1. What about here? Can you integrate this one? T dv over T? Can you integrate that? No, we can't, because that looks too complicated. We do not know the relation between PV. We do not know the relation between PT. We do not know the relation between T and V. So we need to find the relation among them. Do you know any equation that has T, T, V together? RT, the ideal gas equation. You are correct. So we have an ideal gas equation. PV is RT. Oh wait, we have a P over T. Can we have a P over T? Yes, you can divide by T. You can divide by volume. So you can divide by television, TV, then what do you get? You can cross V out, you can cross T out. So this equation becomes P over T is R over V. So we have a P over T. Can you replace this P over T with R over V? Yes, we can. Then this equation becomes S2 minus S1 is CV integral 1 to 2 dt over T plus. Now, instead of P over T, what we have? R over V. Integral from 1 to 2 R over V dV. Right? Then, is this a constant or a variable? What is the name of this R? Constant, gas constant. So it comes out. Now, can you integrate this one? Can you integrate this one? Yes, because we know how to integrate dx over x. Now we know how to integrate dt over t, dv over v. It's going to be cv natural log t2 over t1, the same format, plus r natural log v2 over v1. So that's how we determine S2 minus S1. Is it difficult? Not much. There's nothing new. We got that TDS relation from the energy balance equation. All we did is using the specific heat equation that we studied in chapter 3 and the ideal gas equation that we studied in chapter 3. Nothing new. Oh, wait. I told you that there are 3 equations. So where is the other 2? In the same way, in the same TDS relation. So let me study this equation one more time. So now T, let me divide by T, temperature times mass. So we have ds is du over T plus TdV over T. And if you look at this specific heat equation, we have a du is a CBDT, and we used it. And there's the other one, dH is a CPDT. Can we use that one? Let's see. Can we use this one? Maybe there is a way. What is the definition of this H? H, by the definition, enthalpy is internal energy U plus flow energy PV, right? What is the differential form of H is U plus PV? The differential form is pretty simple. Add D in front. dH is going to be du plus dPV. Oh, wait. What is dPV? Do you know that? If you don't, let me tell you. D of xy is going to be x dy plus y dx. Mathematics. You can memorize that. Then dPV is going to be what? PdV plus VdP. Oh, wait. I saw PdV somewhere here. VdP, I never seen it. So let's move this one to the other side. So dH minus VdP is du plus PdV. No problem, right? Then, now let's go back to this equation. You see one thing, du plus PdV. du plus PdV. Can you replace this du plus PdV with dH minus VdP? We can do that. So ds is this time dH minus VdP over T. So this equation, they are the same. Now, instead of integrating this one as we did here, can we integrate this one? Yeah, why not? Let's do that. Now we know how to do that using specific equation and ideal gas equation. We can do that. Integrate from 1 to 2. Integrate from 1 to 2. Integrate from 1 to 2. Okay, what is the integration of ds? Simple, S2 minus S1. Okay, no problem. S2 minus S1 is, can you integrate dH over T? We can't. So, can we replace this dH? Yes, because dH is Cp dt. So we can say this one is Cp dt over T. What about this V over T? Wait, previously when we had T over T, we used the ideal gas equation. Now we have a V over T. Can we use ideal gas equation one more time? Maybe yes, no problem. TV is RT is the ideal gas equation. Now we have a V over T. V over T over T. Now we have a P. Oh, I don't like P. Let's divide by P. Let's divide by P. Then this one, and cross them out. So V over T is what? R over P. Wait, there's a V over T is what? R over P. So this one is integral from 1 to 2 R dP over P. Now, we assume that Cp is constant. Can come out? Yes. R is constant because the name is gas constant. Come out? Yes. Then can you integrate dP over T? dt over T? Yes. dP over P? Yes. So S2 minus S1 is Cp natural log T2 over T1 minus R natural log P2 over P1. So this is the second equation. Then what is the last one? Oh, for these two equations, we got these two equations assuming specific heats are constant. But not always we can assume constant specific heat. What about if we cannot assume specific heat is constant? So the specific heat is not constant. Then can you solve this one? No. Then if you cannot solve this equation, what do we do? When you have a phase change material, can you solve their properties by an equation? No. So how did we evaluate their properties? Table. So you cannot evaluate this one. Then what do you do? Table. So we cannot solve this one. So S2 minus S1 is going to be S degree 2 minus S degree 1. We can find them from a table. Minus the rest of them is the same. R natural log P2 over P1. This S degree can be found from table. So these three are the equations that we can use when you have a pure gas system. Yeah. After they wrote them down. Okay. Oh, maybe I can put this one on auction, eBay. So then now there are three equations. What you are going to do? Write them down on your formula sheet. If you know the volumetric change, if you know the information about the volume of the system, use the first equation. If you know the relation between the pressure between the initial state and the final state, use this equation. If you cannot assume constant specific heat, use the table using this equation. That's all for today. Any question? No? Then now we can have it. Then see you on, oh, right. We have an exam this Thursday, right? Oh, next Tuesday? We said this Thursday, but if everyone agrees, then I can move it to next Tuesday. Let's do both. Give me 1 minute. So, how many of you want to have an exam this Thursday?